An overcrowded junction box, particularly one that is only 12 cubic inches but is already 60% filled by the factory, can create heat buildup and safety concerns when additional wires are added during installation. Underwriters Laboratories or UL listing is a safety certification. It indicates that the product has undergone testing and meets certain safety requirements. However, it does not guarantee a perfect design or prevent potential issues that may arise during installation or use. There are several possible reasons for a design that leads to overcrowding in the junction box. Firstly, manufacturers often prioritize compact designs to meet customer preferences for smaller fixtures that fit well in various bathroom spaces. Secondly, in the case of an addition to a home, there may be limited space available for a larger junction box, forcing the use of a smaller one. Thirdly, using a smaller box and fewer components can reduce production costs for the manufacturer. There are several solutions to address the issue of an overcrowded junction box. Firstly, consider installing a larger junction box, such as an 18 cubic inch box, to provide ample space for wiring and makeups, ensuring better heat dissipation and safety. Secondly, evaluate whether it's feasible to rewire with number 14 American wire gauge or AUG wire instead of number 12 AWG wire to reduce the number of conductors in the box, making more space available. Thirdly, utilize wire splice kits with compact designs to minimize space consumption within the junction box. Fourthly, consider exploring alternative fixtures that have a larger junction box or a different wiring configuration that avoids overcrowding. Additional considerations should include the following. Firstly, inspect all wiring to ensure that all connections are secure and made correctly, reducing the risk of loose connections and arcing. Secondly, use proper electrical conduit to protect the wires from damage and provide insulation, enhancing safety and code compliance. If there's any discomfort or uncertainty about working with the electrical wiring, it's always best to consult a licensed electrician for assistance. They can ensure the installation is done safely and in accordance with local electrical codes. Regarding the wire gauge and ampacity, the ampacity of a conductor refers to the maximum amount of electrical current it can carry without exceeding its temperature rating. The National Electrical Code, or NEC, provides tables that specify the ampacity of different wire gauges based on their insulation type and operating conditions. For example, NEC Table 310.15. B16 typically lists the ampacities for conductors rated up to 600 volts. Common ampacities for copper conductors are as follows. Number 14 AWG copper wire is typically rated for 15 amps. Number 12 AWG copper wire is typically rated for 20 amps, and number 10 AWG copper wire is typically rated for 30 amps. These values are for typical insulation types like THHN or THWN under specific installation conditions. The 80% rule is a guideline used to prevent overloading electrical circuits. It states that the continuous load on a circuit should not exceed 80% of the circuit's overcurrent protection device, such as a circuit breaker or fuse. For example, if a circuit is protected by a 20 amp circuit breaker, the continuous load should not exceed 16 amps, which is 80% of 20 amps. This rule provides a safety margin to account for factors like heat buildup and variations in voltage. The NEC provides guidelines for box fill calculations to ensure that electrical boxes are not overcrowded, as specified in NEC section 314.16. These calculations take into account the number and size of conductors, device yokes, and internal cable clamps present in the box. Each conductor and device is assigned a volume based on its size, and the total volume of all items in the box must not exceed the box's listed volume. For example, each number 12 AWG conductor counts as 2.25 cubic inches in the box fill calculation, while each number 14 AWG conductor counts as 2 cubic inches. Device yokes such as switches and receptacles are typically counted as 2 conductors based on the size of the conductors connected to them. Internal cable clamps are counted as 1 or more conductors depending on their type and location. The NEC specifies minimum distances for mounting electrical boxes from combustible materials and from other boxes, and also sets standards for the materials, construction, and installation of electrical boxes, including grounding requirements and support methods as specified in NEC Section 314. These requirements are intended to ensure electrical safety and prevent fire hazards. Firstly, electrical boxes must be securely mounted to a structural surface or support to prevent movement or strain on conductors. Secondly, boxes must be mounted at least 0.25 inches away from combustible materials unless they are specifically listed for direct contact with such materials. Thirdly, when multiple boxes are installed side by side, they must be mechanically joined or spaced according to NEC guidelines. Fourthly, boxes must be made of durable materials suitable for the environment in which they are installed, such as metal or non-metallic materials listed for electrical use. There are various types of wire connectors available for making electrical connections, each designed for specific applications and conductor types. Wire connectors, also known as wire nuts, are commonly used for splicing solid or stranded copper conductors in dry locations. Pushing connectors are designed for making quick and easy connections with solid copper conductors, typically in residential wiring. Terminal blocks provide a convenient way to connect multiple conductors to electrical devices or equipment, often used in control panels and industrial applications. Split bolt connectors are used for making high-pressure connections between large-gauge conductors, commonly used in grounding and bonding applications. Insulated connectors provide insulation and protection for splices, commonly used in damp or wet locations. When selecting wire connectors, consider the following factors. Firstly, ensure that the connector is listed and labeled for the specific conductor types and sizes being used. Secondly, select connectors that are suitable for the environmental conditions in which they will be installed, such as dry, damp, or wet locations. Thirdly, choose connectors that are easy to install and provide a secure and reliable connection. Fourthly, consider the space constraints in the electrical box and select connectors that fit comfortably without overcrowding. The NEC requires that all electrical boxes be properly grounded to provide a path for fault current and minimize the risk of electric shock, as specified in NEC Section 250. Grounding can be achieved by bonding the metal box to a grounded metal raceway system or by connecting a grounding conductor to a grounding terminal inside the box. Non-metallic boxes must also be provided with a grounding conductor for connecting to equipment grounding conductors. Proper grounding techniques include the following. Firstly, ensure that all metal boxes are bonded to a grounded metal raceway system or equipped with a grounding terminal for connecting a grounding conductor. Secondly, use grounding screws or clips specifically designed for grounding electrical boxes. Thirdly, when using non-metallic boxes, provide a grounding conductor for connecting to equipment grounding conductors. Fourthly, ensure that all grounding connections are secure and made according to NEC guidelines. The ampacity of a wire is the maximum amount of electrical current it can carry safely without overheating and damaging the insulation or the conductor itself. The ampacity of a wire depends on factors such as the wire gauge, insulation type, ambient temperature, and installation conditions. The NEC provides tables that specify the ampacity of different wire sizes and insulation types under various conditions, as specified in NEC Table 310.15. 16. It is important to select the appropriate wire size and ampacity for the intended application to ensure electrical safety and prevent overheating or fire hazards. Directing factors are adjustment factors that are applied to the ampacity of a wire to account for factors such as ambient temperature, number of conductors in a raceway, and conductor bundling. The NEC provides tables and guidelines for applying directing factors in various situations, as specified in NEC Section 310.15. Directing factors reduce the allowable ampacity of a wire to ensure that it does not overheat and cause damage or fire hazards. It is important to apply directing factors correctly to ensure that the wiring system is safe and compliant with the NEC. The proper way to make electrical connections inside an electrical box involves several steps to ensure safety and reliability. Firstly, turn off the power to the circuit at the circuit breaker or fuse box before working on any electrical connections. Secondly, strip the insulation from the ends of the wires to be connected, using a wire stripper tool to avoid damaging the conductors. Thirdly, twist the bare ends of the wires together tightly, using pliers or a wire twisting tool to ensure a solid mechanical connection. Fourthly, apply a wire connector, such as a wire nut, to the twisted wires, twisting it on tightly to ensure a secure and insulated connection. Fifthly, neatly arrange the wires inside the electrical box, being careful not to overcrowd the box or put strain on the connections. Sixthly, secure the electrical box cover or device to the box, ensuring that it is properly grounded and that all connections are protected. Common mistakes to avoid when making electrical connections include the following. Firstly, failing to turn off the power to the circuit before working on the connections, which can result in electric shock. Secondly, stripping too much or too little insulation from the wires, which can result in exposed conductors or loose connections. Thirdly, not twisting the wires together tightly enough, which can result in poor connections and overheating. Fourthly, using the wrong type or size of wire connector for the application, which can result in unreliable connections and safety hazards. Fifthly, overcrowding the electrical box with too many wires or connections, which can result in overheating and damage to the conductors. Sixthly, failing to properly ground the electrical box or device, which can result in electric shock hazards. The NEC provides specific requirements for the installation and support of electrical boxes to ensure safety and compliance as specified in NEC Section 314. Electrical boxes must be securely mounted to a structural surface or support, such as a wall stud or ceiling joist, using appropriate fasteners and hardware. Boxes must be installed in a manner that provides adequate access for wiring and maintenance. Boxes must be supported independently of the conductors or cables entering the box. Boxes must be installed level and flush with the finished surface. The NEC also provides guidelines for the spacing and arrangement of electrical boxes in various applications. The selection of the appropriate size and type of electrical box for a given application is crucial for ensuring safety and compliance. Electrical boxes are available in various sizes and shapes, each designed for specific purposes and wiring configurations. The size of the box must be sufficient to accommodate the number and size of conductors, devices, and fittings contained within the box, as calculated according to NEC guidelines. The type of box must be appropriate for the environment in which it will be installed, such as dry, damp, or wet locations. Metal boxes are typically used for surface-mounted applications and provide good mechanical protection for conductors and devices. Non-metallic boxes are typically used for recessed applications and are resistant to corrosion and moisture. The choice between using metal and non-metallic electrical boxes depends on several factors, including the application, environment, and local code requirements. Metal boxes provide better mechanical protection for conductors and devices and are required in certain applications, such as hazardous locations. Metal boxes also provide better shielding against electromagnetic interference. Non-metallic boxes are resistant to corrosion and moisture and are often used in damp or wet locations. Non-metallic boxes are also lighter and easier to install than metal boxes. The NEC permits the use of either metal or non-metallic boxes in most residential and commercial applications, provided that they are installed in accordance with the code requirements. Proper wiring techniques for installing a bathroom fan, light, and heater combo involve several steps to ensure safety and compliance. Firstly, turn off the power to the circuit of the circuit breaker or fuse box before working on any electrical connections. Secondly, run the appropriate size and type of electrical cable from the circuit breaker to the location of the fan, light, and heater combo, following NEC guidelines for cable routing and support. Thirdly, install an electrical box at the location of the fan, light, and heater combo, ensuring that it is securely mounted and properly grounded. Fourthly, connect the electrical wires to the fan, light, and heater combo, following the manufacturer's instructions and NEC guidelines for wiring connections. Fifthly, install the fan, light, and heater combo according to the manufacturer's instructions, ensuring that it is properly secured and ventilated. Sixthly, test the installation to ensure that it is working properly and that all connections are secure and properly grounded. Common wiring configurations for bathroom fan, light, and heater combos include the following. A single switch configuration where all functions, fan, light, and heater, are controlled by a single switch. A multi-switch configuration where each function, fan, light, and heater is controlled by a separate switch. A combination configuration where some functions are controlled by a single switch and others are controlled by separate switches. The choice of wiring configuration depends on the desired level of control and the available wiring infrastructure. The NEC provides specific requirements for the wiring of bathroom fan, light, and heater combos to ensure safety and compliance, as specified in NEC Article 422. The wiring must be done in accordance with the manufacturer's instructions and NEC guidelines for wiring connections. The wiring must be properly grounded to minimize the risk of electric shock. The wiring must be protected from physical damage and moisture. The wiring must be installed in a neat and workmanlike manner. The NEC also provides guidelines for the sizing of conductors and overcurrent protection devices for bathroom fan, light, and heater combos. The use of appropriate wire connectors and splicing techniques is essential for ensuring safe and reliable electrical connections. Wire connectors, such as wire nuts, are used to join two or more conductors together inside an electrical box. Wire connectors must be listed and labeled for the specific conductor types and sizes being used. Wire connectors must be installed according to the manufacturer's instructions and NEC guidelines. Splicing techniques such as soldering or crimping may be used to join conductors together, provided that the splices are properly insulated and protected. The NEC provides specific requirements for the installation and use of wire connectors and splicing techniques to ensure safety and compliance. Understanding and applying NEC guidelines for box fill calculations, conductor ampacity, and equipment grounding is essential for ensuring electrical safety and compliance. Box fill calculations are used to determine the maximum number of conductors and devices that can be safely installed in an electrical box, as specified in NEC section 314.16. Conductor ampacity is the maximum amount of electrical current that a conductor can carry safely without overheating, as specified in NEC table 310.15. V16. Equipment grounding is the process of connecting electrical equipment to the earth to provide a path for fault current and minimize the risk of electric shock, as specified in NEC Article 250. By following NEC guidelines for box fill calculations, conductor ampacity, and equipment grounding, electricians can ensure that electrical systems are safe, reliable, and compliant with code requirements.